Respected professors and my dear friends, today I am going to give a presentation on the topic of next generation lithography, the synergy of physics and AI in computational lithography. The contents of my presentation are as follows. Now let's discuss what is lithography. Lithography is a process of transferring pattern onto a substrate using mask or template. And computational lithography is an important area of research that plays an important role in the continued scaling of semiconductor manufacturing process technology. The goal of computational lithography is to improve silicon printability through numerical computing methods including lithography modeling, resolution enhancement, optical proximity corrections, and source mask optimization. This presentation focuses on two specific aspects of computational lithography: lithography modeling and mask optimization. Current solutions to these problems are limited by CPU computing capabilities and optimization algorithms. Previous research has proposed using machine learning for lithography modeling and mask optimization. Now let's understand how machine learning can enhance the computational lithography with an example. The example I am taking is of EBL lithography that is used to integrate in-gas quantum dots into circular Bragg grating resonators. Here, cathode luminescence maps is intentionally altered to varying brightness level of the emitters and to train the ML algorithm, and in the result it was seen that there is a significant increase in photon extraction efficiency in ML enhanced in situ EBL. In the first graph, the theoretical efficiency limit of 43% shown by the blue line is achieved for an etching depth of 430 nanometer. In experiment, a depth of 520 nanometer was achieved, leading to a slightly lower simulated efficiency of 35% as shown by the green line, which is reached for best structures. The red and black lines in the graph indicates a strongly improved photon extraction efficiency of ML enhanced in situ EVL at low mapping doses if compared to conventional in situ EVL. The next figure shows the fraction of optically active devices. Here it can be easily seen that red and black lines serves as a guide to strongly improve process yield of ML enhanced in situ EVL at low mapping doses compared to conventional in situ EVL. Now let's discuss what is AI based computational lithography. As we have discussed previously, previous research has proposed using machine learning for lithography and mask optimization, but the biggest challenge is the lack of data. Also, CPU based lithography optimization require many thousands of CPU running for days to tape out a modern chip. However, AI assisted GPU based computational lithography solution can improve yield of fabricated chips as it lowers as it improves the efficiency. Now, to address the challenge of lack of data, physics inspired AI solutions have been proposed recently that can improve both runtime and quality. Next, let us discuss what is physics-based neural networks. There are various design methodologies for designing physics-inspired neural networks. First is the observational bias, which can be directly learned from data or data sets with underlying physical properties. That is, we are just learning from the data or data sets the physical properties. The second methodology is inductive bias, which brings physics into neural network architecture design to allow strict constraints in the machine learning system. And the third is learning bias methodology. A learning bias methodology which focuses on specific loss function and inference flow that reflect real physical constraints. So far we have discussed physics-based neural networks. Uh, now I am not going deep into the physics-based neural network, but let us discuss an operator which is extensively used in physics-based neural network. Uh, we know finite element methods and finite difference method involve discretizing space, which leads to trade-off between speed and accuracy. uh, and we know we and if someone is familiar with TCAD like Silvaco or Centaurus, then he will be knowing that the speed and accuracy depends on the meshing. That is, if our meshing is very fine, then it will take more time, but the accuracy is very high. Similarly, if the meshing is not very fine, then the simulation will take less time, but the accuracy will also drop. Thus uh, and it is noted that complex partial differential equations are the basis for our TCAD models, and for TCAD models and many other models which required fine discretization, which makes traditional solvers very challenging and time consuming. However, data-driven methods like machine learning can learn the trajectory of equations directly from the data, which makes them faster than conventional solvers. Uh, Fourier neural operator is one such operator, and it is useful for physics-based neural networks for computational lithography. To understand Fourier neural operator in a quick and easy fashion, let us take an example. Let us see that an equation for deep neural network. Here U is the output layer and V is the input layer for the Fourier neural operator. Also look into the diagram. Here W is the bias, which is not shown in the equation. And the Fourier neural operator K is formulated as convolution, and it can be implemented using Fourier transformation. That's all. That's all is the Fourier neural operator. Uh, Now, what are the steps for litho-guided self-training? At first, we have to train the machine learning model with the initial training set where masks are generated from the inverse lithography technique. Then we have to perform the model inference on the training set and obtain the model generated mask. Uh, then we compare both ML mask and the inverse lithography technique mask by using a lithography simulation engine to measure the resist quality. If the machine learning generated mask has a better resist quality than the inverse lithography technique created mask, then it will replace it in the training set, and this steps goes on until we reach the optimum result. Here is a comparison between a rigorous inverse lithography technique generated mask and machine learning enhanced inverse lithography technique generated mask. We can see that both are pretty much similar, but machine learning inverse lithography technique generated mask achieve this 15 time more faster than rigorous inverse lithography technique. Thus it improves the efficiency. Now the conclusion. We can conclude from all the previous slides that lithography modeling and mask optimization are two critical aspects of computational lithography that can benefit from integration of AI. Also, AI-assisted computational lithography solutions have the potential to improve the quality of the result and reduce runtime significantly, as we have seen earlier. While the biggest challenge is the lack of data, recent research proposes that physics-inspired AI solution can address this challenge. These are my references. Thank you.